Okay, chapter 3, part 2. We have covered all the vector algebra in the previous part and then discussed projectile motion in details. We figured out that projectile motion is made of two independent motions. One is horizontal, the other one is vertical. And good news, time goes the same way for both dimensions. And we ignore a resistance, and it's only the gravity that creates the projectile motion. So for gravity, we know it creates free fall acceleration, and it's a constant value, 9.8 meters per second, directed towards the center of Earth, which is usually downward on your sketch. And you can calculate all the parameters from kinematics like position, time, velocity, acceleration at any moment of time, just by solving two problems simultaneously. One problem for x components, one problem for y components, and the time is the same for both components. So it's easy to get all the answers for such motion. Now, this little section shows you a very important result from the analysis of the projectile motion. If you want to combine x and y components all together, because we have v sub x, v sub y, x by itself, y by itself. So four equations, but they're separate. X is x, y is y. But as long as it's a system of equations with time being the same for both components, you can actually solve for time, like substitute for time, and get the solution for what we call the trajectory. Trajectory is the path that moving object follows through space. And you can see from the diagram that the projectile's trajectory is always an upside down parabola. And if you want proof for that, like rigorous mathematical proof, then I have this little equation for you. And you can see that y component, the vertical position at any moment of time, is connected to the x component. And for x component, you can see that x goes squared as the highest power, and then there is a negative in front, the coefficient for this term. So what do we see? We see a classic quadratic equation, ax squared plus bx plus c equals to 0. And y is, of course, not necessarily 0. It can be any other number. The tangent is just a constant. This would be your coefficient b, bx, right? And this negative g over 2v sub 0 cosine squared, this is still a constant. This is just a number. So this is your a coefficient. So it's negative ax squared plus bx. That's what we have as a result of the analysis when time is excluded. You want to get rid of time parameter and just want to solve for y in terms of x. That's what you're going to get from the projectile motion equations. The most general form, you see that it is indeed upside down parabola. Your a coefficient is negative. That means that it's an upside down parabola. X squared shows you that it's indeed the parabola. And your c coefficient, like I said, can be any number. You can play with the vertical position and just transfer that number to the other side and set it equal to 0. So either way, you can find the vertex of this parabola. You can find the intercepts and use it for your trajectory analysis for any given point at any moment of time. I want to point out that we still ignore air resistance. Only one force acts on the projectile motion. It's the gravity. Gravity that creates this constant free fall acceleration. So what you see on the diagram is confirmed by solving the system of 4 equations, 2 for x and 2 for y coordinate. And once you eliminate the time, that's the result. And you see that it's an upside down parabola. If at some point you want to include air resistance, and that's what you probably want to do once you go and solve real life problems as engineers, you have to understand that friction always slows you down. Air resistance is like friction, and friction always steals your kinetic energy, converts it into heat, which we'll discuss later in the course. And with that, you definitely will get less of a range that was covered, less altitude that you reach, and other parameters will also be different. At this level, we're not going to do any of that, but keep in mind that in general, air resistance reduces the x and y components because you introduce an extra force that creates extra acceleration in the opposite direction, and that means you're going to slow down. Okay, question to you. Ball is hit to the outfield during its flight. So we have a projectile motion, right? Because once you hit the ball, once the ball leaves the bat, baseball bat, for example, the only force that acts on the ball is gravity. And gravity creates the free fall acceleration that we already know. So what happens to the horizontal component of velocity? So horizontal component of velocity, let's go back to our analysis for horizontal motion. What do we see? That's the general equation, and that's the x component for the velocity at any moment of time. You see that it is your initial velocity x component. And then remember how free fall acceleration is perpendicular onto the x-axis. And every time a vector is perpendicular onto a certain axis, that component on that axis is 0. So no matter what the moment of time, your velocity doesn't change. It stays exactly the same throughout the flight. So because acceleration is perpendicular onto x, there is no change to velocity with respect to the x component. No matter what the time is, your velocity stays constant. And we actually have another diagram for this. See how the x component here is a certain value, and sometimes later the length of the vector is the same, and it's still the same, and it's still the same, and it stays the same up until it hits the ground. So your x component of the velocity never changes. Once again, why is that so? Because the acceleration vector is perpendicular onto x-axis. So the answer is C. Now, how about the vertical component of the velocity? What do we have for the vertical component? Well, let's go back to our analysis from the previous part. Here we go. That's the general equation. And that's the y component. What do we see? We see that it's not v sub 0, but v sub 0 sine theta, because we're talking about opposite component. And now we do have the acceleration. We have negative g as the value. So what do we see? The more the time passes by, the more value you're going to subtract from your initial value. So it was certain value as the initial one, and then as time goes by, you subtract more and more and more, so you will end up with less and less and less of a value. And let's take a look at the diagram. What do we see? We start with some kind of a positive value, say, I don't know, 100 units, and then later on, see how it's still positive, but a much less of a value. And eventually we hit the maximum altitude. And what do we see at this altitude? Your vertical component of the velocity is 0. You momentarily stop in terms of the vertical velocity, vertical component for the velocity vector. And then you go back to the ground, and your vertical component is getting less and less and less. You're going into a negative value. And because acceleration is downward, you eventually hit the ground, and that's the end of the projectile motion. So, horizontal component stays constant, and vertical component decreases with time. The more the time goes by, the less the value you will end up with. Should make sense. Let me know in the chat if something's confusing. Oh, we actually have more questions. Let's take a look. What is the horizontal component of the acceleration? Well, horizontal component of the acceleration is 0, because acceleration is vertical. It's only the vertical component that acceleration has. And for horizontal, it's 0, because it is perpendicular onto x-axis. No horizontal component for acceleration. So the answer is B. 0 at all times. What is the vertical component of the acceleration? Okay, vertical component. If y goes upward as positive, then g will be a negative value because it's pointing in the opposite direction. So if it's opposite direction, it's negative. And what's the value for g? It's 9.8. We watched the video on that, and we're going to do the lab experiment to prove that it's 9.8, close to 9.8 meters per second. So it's never 0, first of all. Don't you ever say acceleration is 0. What can be 0 is the vertical component of the velocity. You momentarily stop in terms of vertical displacement, and it's just a 0 instantaneous velocity at this point, only for the y component of it. But acceleration is still the free fall. Acceleration is the change in velocity. Remember that acceleration has nothing to do with velocity by itself. It's the change in velocity. And there's always a change. That's the reason for the projectile motion to actually go back to Earth. If acceleration is 0, then there is no change, and the projectile would just fly into space. Because there is no change to that motion, it will just keep on going on and on and on and just leave the Earth and go all the way through the Milky Way galaxy and beyond. So acceleration is never 0, and do not say that velocity is same as acceleration. It's not. Okay, so negative 9.8. Be careful. If you, for some reason you choose your y to be downward as positive, then it's going to be a positive 9.8 value. If you decide to flip-flop the coordinate axis for some reason, then your g will be positive 9.8. So it really depends on the choice of axis. Okay, last topic for chapter 3, relative velocity, a very important one. You will use that, what we call Galilean transformation, over and over again for other things in physics. So pay attention, focus, and try to understand what's going on here. So we have a problem with measuring velocities because remember, you can be on the train moving at a certain rate in a certain direction, or you may be just standing on the ground and you'll be looking at the passing train, and then it's going to be a different result. So if you're on the train and you're just chilling, and the reference frame is the train itself, you're not really going anywhere. You're just, sitting still. But if you're a bystander, then it's going to be like 65 miles per hour, convert that into meters per second and stuff like that. So for any vector, specifically velocity, you really want to specify, or at least keep in mind, the reference frame that this velocity applies to. Say, this is a classic example that should clarify what I'm talking about. You got velocity, and the first subscript represents the water, and S means the shore, so the ground. The ground that is not moving anywhere. So how fast velocity of water, so how fast the water moves with respect to the ground. So essentially it's the speed, the velocity of the current. Which way is the current? The river current. So which way and how fast does the river flow? And you see that on the diagram. So VWS shows direction to the left, leftward, because this is the direction for river current. So this is the direction for flowing water with respect to the ground. What you can also discuss and solve for is velocity of the boat, which has a subscript B, and S is also the shore. So this is how boat travels with respect to the ground. And the last option is boat with respect to water. So what you see on the diagram is a vector sum of two vectors that produces the actual sum. And that is how you can calculate motion with two different reference frames. So there is a reference frame for, say, the ground, the shore. And then there is the river that moves. And you are on the third object, the boat, that is going in a certain direction. And you want to know how the boat will behave with two different kinds of motion. The first motion is with respect to the water. See how it's going to just go across the river. And the resulting motion with respect to the ground, like what you're going to measure if you are on that boat. And you see how you're going to be traveling at a certain angle with respect to the river current. And if you want to predict where you're going to end up on the other side of the shore, you definitely want to consider this vector sum for your solution. So here is a little trick for you to memorize which subscript works for whichever problem you have in mind. So what you see here is called the Gaussian transformation. And the trick is, for any two subscripts that you want to work with, say A and B, you have to put the first subscript on the first place. And then there is a blank spot for something else. And then the second subscript, you put on the last spot. And there's still a blank space for the third component for the transformation. So let's say you have whatever is the third object that you want to include in the Gaussian transformation, say N, object N, and N will fill in those two blanks. So AN plus VNB, N kind of cancels, and you're left with A and B. So once again, you have four spots, four subscripts to think about, and your first subscript that you want to end up with goes to the first spot. Your second subscript goes to the last spot, and the two spots in between are taken by the third component for the Gaussian transformation. Let's go back and see how this works for the river current, boat, and the shore equation. I want boat with respect to the shore, and I also have water to take care of. So boat goes to the first spot, shore goes to the last spot, and water, stuff that I don't want. See how I want boat with respect to the shore. I don't want water to be present in my final answer at all, but I still have to include it into my solution. So water goes in the middle, the second and the third spots out of the four spots that you see. Water cancels, if you will. Second and the third spot cancel, and you have B and S as your final result. Very easy and straightforward way to memorize Gaussian transformation, and it helps you to solve also many problems when you have multiple reference frames to work with and motion with respect to one frame, one system can be connected to the other system. Now, it's very important to remember that for vectors, you can't flip-flop subscripts for no reason. If you got A with respect to B, you can't say it's the same as B with respect to A. And I'll prove it to you right away. If you say water with respect to the shore goes to the left, then shore with respect to the water will actually go in the opposite direction. Have you ever noticed how, let's say you are on the train, moving train, what do you see in the window? You see how all the houses, all the trees outside of the train, they do what? They move backwards. So let's say you can't tell if the train is actually moving or it's like the whole thing is going backwards. You will never notice the difference. You would say, oh, the train is sitting still. and everything that I see outside is actually going backwards. Yeah, it's your common sense that tells you, yeah, houses cannot move backwards. But let's say you're on a rocket going through space and you see a planet passing you by. You say, oh, it's actually the planet that goes backwards, right? You can totally see that happening. So the point is, if you got water with respect to the shore in one direction, then shore with respect to the water will go in the opposite direction. And if you still want to equalize them, set them equal to each other, you have to add a negative sign in front. So A with respect to B is not the same as B with respect to A, but A to B is exactly the opposite of that. So once you introduce a negative to one of the sides of the equation, you can set them equal. And we'll solve some problems, and you'll see how this works. This is a very useful trick to solve problems, because sometimes for a problem, you are given the opposite connection for those subscripts. It's not going to be A to B, A with respect to B, it's going to be B with respect to A. Not a big deal. You add a negative to that given, and you can solve the problem with that extra negative. So you will not be adding vectors, you'll be subtracting them. Remember, subtraction of vectors is adding the opposite, so not a much of a change in terms of solving that kind of problem. Okay, that's it for chapter 3. I'm gonna pause the recording and we'll move on to classroom discussion.